Started.
Yeah, thank you. Yeah. Um, so I said, yeah, so we'll be looking at seismic and aseismic deformation in geothermal and hydrocarbon, and I will highlight two studies, one in California and one in Nevada. And so this study in Nevada is chiefly done by my student, Roshan Karala. We published this late last year. He's done a really good job on analyzing the seismicity and INSAR. And then I'm working with a postdoc in Potsdam, in Germany, Valerian Schuster. He's done a really phenomenal job on analyzing core data from this geothermal reservoir. I won't have time to go into details today, but if you're interested, I would be more than happy to talk about that. Huyun Gu, so the second half, so to speak, of the team is over at the University of California, Santa Cruz, and this is Huyun Gu and Emily Brodsky, and they were working on using tidal analysis to infer permeability in the reservoir. So just want to acknowledge all the collaborators. This is funded by the Department of Energy, and they've been supporting us for several years now. Okay, so let's jump in. Um, I thought since we have a geographically sort of diverse audience, I can sort of review a little bit what happened in the US, which I personally, looking back at how induced seismicity unfolded in the central US, it's just very interesting. It's just very unexpected. So I put a very unprecedented increase in induced earthquakes in Oklahoma and Texas, and it started in the late 2008s, 9s here. So this is a map of Oklahoma, indicated here in black, and we're showing wastewater disposal wells as blue triangles, and then the earthquakes are circles, magenta and red circles. And overall, before 2008, there was some activity. There were some magnitude fours, but more in the southern part. And the oil-bearing zones are all central and north, so this is very flat farming and oil country, and not a whole lot of activity. That changed first in 2011. The Prague earthquake in magnitude 5.6 happened very close to Oklahoma City and caused actually some damage at the University of Oklahoma. And then even more drastically between 2014 and 2016. So basically the whole central and northern part of the state lit up with earthquake activity. And you can see this pretty nice spatial match where the wastewater was disposed of and where the earthquakes happened. More recently, another interesting earth. So between 2014 and 16, there were well, actually, they were all in 2016. 2016 had three magnitude 5 earthquakes. So these are the white stars. Then another one in 2024, close to the first Prague earthquake. Um, and then more recently, Texas is almost mirroring the activity in Oklahoma. So very interesting, just the western part of the state where the Permian Basin, a very large unconventional oil and gas reservoir, so very heavy sort of enhanced recovery techniques and a lot of saltwater disposal. And so we now have six magnitude 5 plus events starting 2020. Then we had two in 2022, one in 23, and two more just last year. So very interesting to see that, and to me, very unexpected. I started working on this in 2013, and in 2013, we were still debating if Prague was natural or induced. And then obviously this happened here 2014 to 16, so that sort of clarified the doubts that the correlation was too strong. And then seeing a similar picture in Texas. So very low pressure operation. Wastewater disposal is, gravity feed. The fluid just sinks in by the hydrostatic pressure. Very low pressure operations can cause earthquakes. So going back a little bit, setting the stage here, what's causing this earthquake activity? And people are debating a little bit how much hydraulic fracturing versus wastewater disposal is contributing. But the key sort of underlying physical process that people usually think about is really motivated, at least partially, by this by this controlled test that was done by the USGS in 69 to 74. Certainly not the only one, but that was one very impactful study that fully demonstrated you can create earthquakes by varying pore fluid pressure in a reservoir, right? So this is shown here just real briefly, right? So the vertical bars is earthquake activity. So this is in the Rangeley, Colorado, in a reservoir where pore pressure was monitored in idle wells and then actively modulated by injecting fluids. So the vertical bars are the earthquakes. This black line is the reservoir pressure, and then this dashed line was computed before the experiment that was determined to be the critical pressure required for activating the faults that are hydraulically connected to this reservoir. And you can see that roughly it works, right? Once you drop below this line, the earthquake activity is decreased. If we're above, then you get more earthquakes, etc. And then it's essentially shut off at the end when pressure was reduced again. So this is basically what we've probably quite used to thinking about, effective normal stress reduction by increasing pore pressure, and that's moving faults closer.
I'm trying to connect my AirPods to my computer.
Okay. And so the pore pressure, and this is interesting to look just at the magnitude of these pore pressures, right? So between 5 to 10 MPa. Now, let's fast forward and get back to Oklahoma. What's the predicted, so this is from numerical models, pressure changes in Oklahoma? Well, they're tiny, right? So from a model that was published by Karen et al. In 2014. And so why are these pressures so small? Well, you're injecting, first of all, at low pressures. You're creating these pore pressure gradients that sort of drive flow to large distances. But if we enforce or require that all of these earthquakes are directly caused by these pressure effects, well, at these large distances, pore pressures have to be very small, okay? So we'll get back to this in a little bit, but I wanted to show just real briefly, well, let me see. We're talking about Oklahoma, right? So I said that a lot of these earthquakes happen at large distances, right? But what else is different in Oklahoma, let's say, compared to Rangeley, Colorado? Well, they're far from wells and they're also very deep, right? So let's step through these two plots here in a minute. So for a minute, so this is a time series of blue are the combined injection rates in wastewater disposal wells in the Arbuckle Formation, which is under pressure, very high permeability formation. It's just a great target to get rid of a lot of these saltwater volumes. And then the gray one are the seismicity rates, and they track each other with a certain time lag on the upswing and then also on the downswing. So the correlation looks quite convincing, but the right-hand figure is quite surprising, right? So this is just a histogram of depth to basement and number of earthquakes. So here's where the Arbuckle is, the target injection zone, and here's where the earthquakes are. So based on this particular relocated earthquake catalog from 2016, there's at least 1-2 kilometer separation to where the earthquakes are, and even probably around 4 to where the peak in the earthquake activity is, right? So a clear sort of space and lateral and vertical separation from the injection activity and where the earthquakes are, okay? Now, if we sort of modify this original effective normal stress reduction and pressure model, and this has been suggested here in 2013, for example, by including faults, we may have an explanation, or at least one potential mechanism, how we can change pore pressures over these very vast distances. And the idea is pretty straightforward. On the left-hand side, it's from Faulkner in 2010, showing what a fault structure looks like. You have your core deformation zone, and then you have this off-fault damage, which are cracks, basically. And these cracks have a certain density that decays as a function of distance. And fracture density is thought to also affect permeability. So if this is correct, and if this holds true even at seismogenic depth, which um, is a whole another discussion, which we may or may not have time to get into. If this holds true, well, then fault damage zones are very effective fluid or pore pressure conduits. And if we modify these numerical models where we have the injection zone here, and then we have a high permeability fault, either directly connected or slightly offset from the disposal, we can see that these pressure contours are pushed downward, and we can perturb pressures even 2 to 4 kilometers beneath an injection zone. There's some evidence that this may indeed be the case, although kind of somewhat indirect. But this is, for example, by Hornback et al. In 2015, showing this is for Texas now that injection in the Ellenberger started seismicity that propagated downwards and occurred on a potentially hydraulically connected fault. Okay, so very similar to this model here. We ourselves looked into this in 2016 when we were looking at the potentially induced sequence in California here in the Central Valley. We saw some systematic migration away from a disposal well, and we ran or constructed a hydraulic model with heterogeneity where we have a high permeability fault damage zone in there. And even if we invoke this, and there's no direct evidence that this high permeability pathway exists, it's just from the seismicity, right? So there are no direct measurements of permeability at these depths. But if this is true, and if we could theoretically speak, keep the permeability this high over these large depths, we would still only get very small pressure perturbations at the hypocenters, okay? So this is very consistent with the Keratin study. So the main idea that even very small, tiny perturbations are sufficient to cause earthquakes, I think is very well accepted and established just based on observation, right? And those stresses and pressures are similar to aftershock triggering stresses. Okay, so there is some consistency between these observations. Now, so for the rest of the talk, I want to go a little bit beyond direct pressure effects, and we'll look at other observations and look at the contribution of direct pressure and then pore-elastic effects for field-wide injection operation. And then in the second part, we'll look at induced seismicity and high resolution measurements at Blue Mountain. So one will be larger scale, and then we'll zoom into one fairly compact geothermal reservoir in Nevada. So let's start with hydrocarbon or oil and gas in California. And we published a study in 2021 on the St. Ardo oil field. This is the youngest oil field in California, just west of the San Andreas Fault. And when we looked at it from a surface deformation, so this is from satellite radar interferometry, we can see the deformation across the San Andreas Fault. So this is good because this is what we expect, right? So we're going from the North American plate to the Pacific plate. So we have a lot of relative motion. So clearly this is the biggest signal, but we also saw some what's interpreted to be uplift right within the center of a bunch of disposal wells here. And this is what it looks like spatially. And then if we look at it over time from 2016 to 2020, so there's about, what is this, six centimeters of uplift within the reservoir. So what's going on here? Well, we think this is really due to large volume disposal that is causing pore-elastic inflation of the reservoir. So this is a simple cartoon where we're injecting fluids at the center and we're increasing pore pressure, and the pore pressure is causing elastic deformation across the rock matrix, and this leads to measurable uplift. So this seems to match what we have here. But it also causes laterally elastic dilational and compressive stresses. So these stresses are compressional at larger distances. So this is in a simple radial symmetric theoretical model, we can look at the displacements and the strains. So it's dilational close or within the increased pore pressure zone, but then we have compressional stresses at larger distances. So this is on linear scales. And I'll show a more complex model here in a minute. But what's going on with the seismicity? Well, so this is interesting as well, right? So we had this kind of bullseye uplift signal, and we think it's related to pore pressure increase and the elastic stress coupling. And we see this seismicity here. So this is a map view of where the injection is happening. And then we have this seismicity cluster extending north from the zone of wastewater disposal wells. Biggest event at magnitude 4.5 local magnitude at some distance. What is this? 5 kilometers or so. The earthquake activity is a time series here from 76 to about 2018. Seismicity is highly correlated with the injection rate in all of these wells. Correlation coefficient is about 0.71. And we also see an interesting power law decay of the seismicity. So this is here and then as a function of distance from the reservoir. And the red one is the seismicity decay. So let's look at these lines here in a little more detail. So this power law-like decay, we actually expect this from elastic stress decay in a poroelastically coupled reservoir. So we run a simple layered model where we're injecting in a reservoir and we're measuring we're modeling what the pore pressure and the elastic stresses are doing in reservoir and basement. And there's a impermeable cap rock, just basically to isolate the processes at depth from any more near surface lithological units. So the pore pressure tends to localize within the injection zone because there's just permeability contrast, permeability being quite a bit higher than in the basement. But if we just focus on this one here, this is pore pressure as a function of distance just here in the basement layer. So in the low permeability zone. And so the blue ones are pore pressure evolution over a couple of months. And for each one, we see a connected elastic stress curve that has this power law elastic stress halo at large distances and has a much larger spatial footprint than the pore pressure alone. So that's interesting. It seems to match what we saw from the seismicity here. We investigated this idea that the spatial decay of seismicity could be indicative of elastic stress versus pore pressure. We validated this idea for a whole bunch of basically point source injectors. We included several from Europe here, which is Basel, St. Gallen, and I don't remember if this is Imsheim or Landau in Germany in the Oberrheingraben. And we saw something that sort of matches our expectations from the numerical model. We had some, and there's also sites in Australia and North America. So some sites had this more abrupt decay. So the blue ones, where we think they are predominantly directly pressure driven, and some look more power law-like. And so the thought is, well, so maybe these have a pretty efficient elastic stress halo. We have a larger spatial footprint, more distant induced seismicity, versus direct pressure sites are a bit more compact in terms of induced seismicity. So this obviously has some implications for seismic hazard assessment, but that's sort of one question for the group, right? How can we deal with these sites where we get induced earthquakes out to very large distances, and the activity sometimes is delayed by 12 months, right? Injecting here and then 12 months later, earthquakes start to pop up at 10 kilometers distance. How can we deal with that from a hazard assessment and sort of risk mitigation point of view? So maybe we can talk about this at the end of the talk. Okay, so let me continue. So this was the basic observation from California. that we see this uplift signal from INSAR, and it does seem to be related to pore-elastic coupling. And if we do include pore-elastic coupling, we do expect induced earthquakes out to larger distances, right? So this is basically the first two points here. Well, what are the problems? Well, in most studies from Oklahoma and our California studies, we're inferring the stress and pressure distribution from numerical models. And in these numerical models, they're very poorly constrained. The numerical models, if you want to do flow and elastic stresses over tens of kilometers, we simply don't have any measurements of permeability, storativity, pore-elastic coupling. So we're sort of inferring something maybe from laboratory or from other studies, but we don't have any direct measurements. So these issues motivated us to do a different study, to do a high resolution study in just one compact area and see if we can untangle some of these underlying processes. Okay. And this is the quite beautiful site of Blue Mountain in Nevada. This is 3 hours from Reno, 3 hours about north of Reno. We're working with seismic data. We installed pore pressure transducers in idle wells, and we also worked with the core data. There's a very large rock core repository that we've been investigating with Vallejo and Schuster at GFZ. So what's Blue Mountain? So it's a compact, sort of mid-size geothermal power plant, binary fluid geothermal power plant. Started operating in 2009 with a gross production of about 50 megawatts. I think they're reaching about half of that currently, maybe a little bit more. And you see some pictures of what things look like. It's fairly arid, which is obviously quite good for us if we want to do INSAR. This site is incredibly interesting because it was the first pilot test for Fervo Energy for their new enhanced geothermal system stimulation technique. So Fervo, I don't know if you call it the news here in North America, but Fervo is basically a company that is using oil and gas techniques in geothermal, and they've been reasonably successful in designing or engineering geothermal reservoirs, which obviously has been tried many times in Europe at Suls and Basel and St. Gallen and Finland and other places. But the main thought here is Fervo is using horizontal drilling and hydraulic fracturing to create fluid pathways between a well doublet and then to flow cold water through hot rock to produce geothermal electricity, right? And so this it's maybe a little bit too early, but the first results seem fairly encouraging, and this may have commercial liftoff pretty soon, to the point of where this is done at very large scale in Utah and in Nevada. Of course, similar type of things have been tried before, and one of the big issues is induced earthquakes. And I'm sure most of you are familiar with South Korea, was it 2017, right? The Pohang earthquake, which are potentially induced by the stimulation of the reservoir, although the earthquake happened a month after the stimulation, where pressure was allowed to bleed off here at the wellhead. But anyways, the observation is there was a magnitude 5.4 close to a geothermal site, and that caused a lot of negative publicity for geothermal. So we'll have to see. Hopefully, we can help mitigate some of these issues here in the US. Okay, so that was a bit of a tangent, but just to highlight, okay, Blue Mountain was the pilot site for EGS, but Blue Mountain is also a fully operational mature geothermal reservoir. And I mentioned this before, we had sort of 4 different pillars of our studies working together with UC Santa Cruz and GFC Potsdam. We looked at the core samples, we measured permeability from pore pressure and tidal forcing. Today I will talk about the seismicity and the surface deformation from INSAR measurements. And I will highlight and summarize the work by my student Roshan Karala, who did a really good job working with a very complicated, noisy seismic data set. So this is the seismic array that we had in Blue Mountain, consisting of 8 stations. Although some of the stations close to the operations were almost unusable. And then we have the production wells and injection wells. So the geothermal reservoir or resource itself is taking advantage of a westward dipping normal fault in the Basin Range tectonic province. So we have crustal thinning and we have higher heat flows in this area. This is why we have a geothermal resource. The original plan was to produce at shallow depth and re-inject at deeper depth, so the water would circle along the normal faults and heat up, and then could be produced, and it could be roughly a balance in terms of pressure and temperature declines should be minimized. That plan had to be adjusted, as you can see. The injection wells had to be moved further away because of thermal breakthrough problems. So I'm not going to be able to explain all the details, but you can see that the operator had to adjust as they were going along. So what does the seismicity look like? Well, it's a very low background seismicity zone, very small magnitude events. The biggest one that we caught was about a magnitude 1.5. And it's focusing at shallow depth and a little bit to the east of the east and south of production and injection zones. So this is the map view here. And Roshan created absolute locations using Nunlin-Log, and then he relocated that using differential travel times away from cross correlations. So you see orange and blue markers. These are not additional earthquakes. They're the same earthquakes, but different locations for the same events. And then you see 2 different cross sections for south, north, west, east. Not strong indication that these are localized or fault bound, looking fairly distributed, both in depth and then laterally, but clearly spatially focused in the reservoir area. Okay. Now, this is interesting here at the bottom. If we look at the magnitudes, we have some background activity, but then we have these vertical streaks where we have higher rates. And so we looked at that and decided to analyze this in more detail. So this is in late 2017 and early 2018. So this is the same observation plotted a little bit differently. Now with the seismicity rate in black. And then we have normalized productions in red. So what's happening here is that the production kind of is fairly stable throughout the year, but the operator has annual maintenance shutdowns where all the pumps are stopped for 24, 48 hours, which happens fairly abruptly. And this is where all the earthquakes are happening. And you can see the 2 right-hand plots. The first shutdown in 2017, where the earthquakes peaked a bit more on the back end of the shutdown period. And in 2018, it looks like it's peaking more at the earlier times of the shutdown. But this is just, as I said, 24, 48 hours. So what's happening? So this observation, a little bit puzzling, right? Because when you stop things, it's somewhat unexpected that you would trigger or induce earthquakes. It certainly doesn't increase temperature or pressures. So we looked at the model that was suggested by Siegel and Liu in JGR in 2015, and then also used by others, where we're not only looking at the direct pressure effects, but we also model how normal and shear stresses are changed due to porolastic coupling, right? And we compute the resulting Coulomb stress, take the time derivative, and then solve this ODE, which is based on Dietrich 1994 on rate and state friction. But this is basically the key thing to remember from this point is that seismicity rate here is related to Coulomb stressing rates. So it's all rate dependent. So how fast you sort of give the fault a kick sort of determines if you get seismicity and how much. Okay. So if we model this, so this is the 2018 shutdown, I believe. The black one is the observation. And then the red one are two different models with two different what is it here? The relaxation time parameters. We can explain our observation in time pretty accurately, and we can see that. So the model, the different components of the model are pore pressure here, right? Then the change in normal stress due to pore elastic coupling and change in shear stress. And the key component is that at some distance, at some bit of offset from where the injection, for example, is happening, um, the pore pressure decreases more gradually than, for example, the normal stress or shear stress. So you sort of get this imbalance of pore pressure effects and elastic stress because they just act at different space-time scales. Elastic stress is being transmitted very rapidly. And that sort of leads to this very short-term peak in the Coulomb stress, this Coulomb stress increase, right? And again, this is what we're using to drive our seismicity rate prediction, right? And so this peak is manifested in here as a similarly peaked seismicity rate over about 1 to 2 days, okay? And how rapidly this decays depends on the characteristic relaxation time. It's basically the rate and state A parameter and the normal stress, okay? Now, so this is what it looks like in time, but it's also very useful to look at this in space. And I found this plot quite instructive. Where at the top, we're looking how Coulomb stress changes in 2017 and 2018. These are Coulomb stress changes only due to direct pressure effects, okay? So it's just basically friction times pore pressure, roughly speaking. So what's happening here? Well, the injection has a negative Coulomb stress change. Well, because when we're injecting, we're creating this peak distribution of pore pressure. And once we stop, right, it decreases most rapidly at the injection well, and then we get this negative. Production, it's the opposite, right? Production is when we're sucking out fluids and we're creating this reduction in pore pressure. And when we stop production, we get pressure recovery, right? So the pressure diffusion, the pressure diffuses in again from the surrounding medium where pore pressure is higher. So it's this artificial pressure gradients produced by pumping out water, and we get a relative increase, okay? But you can see that the spatial extent is pretty modest. And well, why is it so small, the spatial extent? Because even for the fairly high probabilities that we measured and analyzed, the time scales are so small, right? This is 12 to 24 hours. You just don't have very far-reaching effects, okay? Now, what does it look like if we include pore elastic coupling? So this is the same 2017, 2018, and the bottom row is with pore elastic coupling. So this starts to become interesting because, again, we see the difference injection and production close to the well. So these are close to the well is basically direct pressure effects. But then we get this red Coulomb stress change lobe at larger distances. Very similar to kind of this elastic stress halo that we saw from the earlier studies, right? It's just saying that elastic stresses are transmitted to large distances much more easily, right? And even out to where the distances where we had these induced sequences, we now see at least a modest degree of Coulomb stress change. Okay, so I think it's a very plausible explanation, right? So that when we include rate-dependent earthquake nucleation and pore-elastic coupling, we can have a plausible model for these induced earthquakes in Blue Mountain. Okay. Now, I'm going to wrap up and just show two more slides here. And these are about the INSAR now. So surface deformation, we did the same here as for California. And as expected, the signal has the opposite sign, right? So the colors here are ground vertical velocity. So this study, we had two different satellite tracks, which allowed us to separate out what are the horizontal and the vertical components. So isolating the vertical only, we see a clear downward, subsidence, right? It's not inflation anymore, it's subsidence, where the fluids are pumped out and circled through the geothermal reservoir. This is a close-in. You see the production wells and this slightly asymmetric geometry, the subsidence zone, and then also a profile across. So we get subsidence rate of about a centimeter per year. Okay. And what's causing the subsidence? I first thought it must be pressure related, but a more detailed analysis actually showed it may not be. It seems that thermal contraction, so we have a temperature decrease of it's about a couple of degrees or so per year. The thermal contraction cooling down the rock and a seismic slip on this normal fault, just a little bit to the east, seems to explain the observation really well. Okay, so let me unpack this a little bit. So on the left-hand side is the observed signal from the INSAR, and you see the contours here. And it's a bit shifted, but a little bit to the sides of the production zone here. And we can match this sort of spatial pattern pretty well with the combined solution that has both thermal contraction and it has a seismic slip. This is an Okada type solution on a fault that is really parallel to the orientation of the known normal fault here. Okay. And so the interesting part is that for this combined inversion, right? So we have a MOGI contraction, thermal contraction source, and a localized Okada source. We're matching the orientation of the normal fault, and we also see that the seismicity may be within the zone of aseismic slip. So these rapid modulations of injection rate may actually also modulate from predominantly aseismic slip to a more seismic component during these brief maintenance shutdown periods. So a lot is coming out by combining the seismic with the INSAR. And I think it's a fairly plausible explanation that the porolastic is contributing to the short-term rate bursts, induced seismic rate bursts. But the long term is aseismic. And, we can do a moment balance from what we expect. So from the operational activity, if everything would be related really seismically, we should have a magnitude 5.1 earthquake. The biggest one that we saw is about magnitude 1.5. The aseismic geodetic moment is about 4.8 or moment magnitude. So it's sort of starting to add up that most of the deformation in this reservoir is aseismic. We just get these short-term modulation and burst in seismic rates. Okay. Okay, so let me wrap up and then I'm happy to discuss and see what comments and thoughts there are, right? But I hope I showed you some evidence that just looking at the direct pressure effects, we're sort of missing a lot of important physics that are creating small induced events and aseismic deformation, etc., right? And so what did we see specifically? The porolastic explains or provided one plausible explanation for how rapid injection rate changes can trigger or induce earthquakes. In Blue Mountain, the contribution from these induced earthquakes is tiny, right? Very small. It was mainly aseismic deformation. And the spatial reach, how far away we can induce earthquakes, that is controlled by the elastic stress contribution, and that also controls the probability of fault activation and maximum magnitude. So this last point, just to show one more summary slide. The last point is basically, if you look at the direct pressure alone, you get a very different spatial function of where you expect earthquakes to be activated or induced. as if you include this elastic stress that decays as a power law, and you have a much larger spatial kernel. And it's the overall probability is the combination of pressure stress perturbation and then the availability of faults. And arguably, the bigger the volume that experiences a perturbation, then you get also higher probability of inducing larger magnitude events. Okay, so I'll leave it there, and happy to discuss and take any questions. Yeah.